Hello, I'm gonna work through the study guide in this video. How many pages is this? 16 pages. Oh my gosh. Okay, so do make sure that you have the most up-to-date version, because there were some typos in the previous one, which would be confusing if you were to do that. Okay, so critical numbers of this function, right? Critical numbers mean that we have to find the derivative and set the derivative equal to 0 and then solve for t. So the derivative here, we're going to use product rule. So derivative of t is 1, so that leaves us with 8 minus t. I'm going to write it like this, 8 minus t to the 1/2. Then if I differentiate that term, I have t times 1/2 times 8 minus t to the negative half. This is chain rule, right? Times the derivative of 8 minus t, which is -1. All right, so if I simplify this, it's going to be 8 minus t to the 1/2 minus 1/2 t, 8 minus t to the negative half. All right, so if I set this equal to 0, then how am I going to solve for this? Maybe first you can rewrite it back into square root form. So this is square root 8 minus t minus t over 2 square root 8 minus t. And if I turn this into a single fraction, so I'm going to try to get the same denominator on both sides, I'll be left with, okay, so I'm going to multiply this by this denominator. Don't know how to explain it. I'll be left with 2 times 8 minus t over 2 root 8 minus t, now that I have a common denominator. So that leaves me with 16 minus 3t over 2 root 8 minus t. And where does this equal to 0? It's going to equal 0 when t is equal to 16 over 3. Okay? So you might think that t equals 8 is also a critical number, but it's not because my domain is defined as t less than 7. Let's find the critical numbers of this function now. So to take the derivative, we'll get 4x cubed minus 44x. Let's factor this. Factor out at x. Let's factor out 4x. I'll have x squared minus 11. And this is simply 4x, x minus root 11 times x plus root 11. So we're going to have 4 critical numbers. 0, root 11, and negative root 11. Locate the absolute extrema of this function on the closed interval. So to do that, let's find the critical numbers first, and then we'll have to test the function at the critical numbers within the interval and also the endpoints of the interval. So here's my derivative, and this is equal to 0 when x equals -3. Okay, so that means I need to test x equals -6. Let me do that. F of -6 is equal to what? 3 times 36 minus 18 times 6 minus 4. So that's 108 minus 108 minus 4, which is -4. Test the critical point, -3. That'll give me 3 times 9 plus, minus 18 times 3 minus 4. That'll be 27 minus 54 minus 4, which is -3, 1. And then the other endpoint is 3 times 36 plus 18 times 6 minus 4, which is equal to 108 plus 108 minus 4, which is 212. So my minimum is -3, -31. My maximum is 6, comma 212. Hope this is correct. Okay, good. Okay, question 4. Remember what the conditions are for mean value theorem, okay? So in order for mean value theorem to be applied, the function has to be continuous and differentiable. So is this function continuous and differentiable on the interval? Remember, it only matters within the interval. So x squared doesn't have any jumps or any corners, so we know it's continuous and differentiable. Okay. So that means mean value theorem can be applied. Remember, Rolle's theorem has one more condition, which is that the endpoints have to yield the same value of the function. But since mean value theorem can be applied, we can go ahead and calculate the derivative. Derivative is 2x. And we're trying to find the value of x, or c, such that 2c equals f of 11. Now f of 11 is 121, minus f of 1, which is 1 squared, divided by 11 minus 1, which is 10. And that is equal to 12, right? So that means c equals 6. Next question. Find the open intervals where this function is decreasing and increasing. So that means we're going to have to find the critical values, right? So f prime of x is 12x minus 3, which means our critical number is x equals 1/4. So our number line can be split like this. We can maybe test a point x equals 0 here. We would find that f prime of 0 is negative. So it's decreasing here. We can test 1 up here. F prime of 1 is equal to 9, which is greater than 0, positive. So that means the function is decreasing from negative infinity to 1/4 and increasing from 1/4 to infinity. Find the critical number of this function. All right, take the derivative, negative 16x plus 48. And this equals 0 when x equals 3. All right, question 7. These graph questions can be tricky, but they just require very simple logic. And then we can do some process of elimination. That's pretty much about it. Okay, so a good first step is to figure out where the derivative is equal to 0, right? So we're given the graph of the function, and we want to find what the graph of the derivative of that function is. So remember, the function is going to have a derivative of 0 when we have relative maximums and minimums. So we know that these points have to yield a derivative of 0. All right. So we're going to look at these graphs here, and we're going to think about which graph crosses the x-axis at those points, at those x values, because the derivative has to equal 0 when x is equal to negative 1.5, 0, and positive 1.5. So which graphs cross the x-axis at those points? D works for that. So D is a possibility, and B is also a possibility because the graph crosses the x-axis. The graph of the derivative crosses the x-axis, where the original graph exhibits an absolute maximum or minimum. So now we just need to narrow it down between B and D. Now we can look more carefully at the slope of the original graph. We can see that the slope of the original graph starts going downwards, meaning that it's decreasing. So the graph shows that we have a decreasing interval from negative infinity to negative 1.5. So that means that the derivative must be negative from negative infinity to negative 1.5. And that tells us that the answer must be D, because only D has a negative value from negative infinity all the way up to 1.5, negative 1.5. So B is not possible. And we're left with only D. So that's a simple process of elimination that you can do in your mind as you're thinking about this question. And on the solution key or the solutions that Miss Lee wrote, you can see a pretty helpful color-coded diagram where the increasing and decreasing intervals of the original derivative, of the original graph correspond to the positive and negative regions of the derivative graph. So think about that and look at the graph carefully. Okay, concave upwards or concave downwards. So that means we have to find the second derivative. Right, so first derivative is negative 18 x squared plus 12x plus 2, which means second derivative is negative 36x plus 12, which means that we have a point of inflection at 1/3, and then we just need to test some values. So we can test x equals 0. That's going to make the second derivative positive, and then x equals 1 makes it negative. So we'll have concave up when we have x between negative infinity and 1/3, and concave down when we're at 1/3 to infinity. So what does that correspond to? E. Points of inflection of this graph. That means we're going to have to find the second derivative. All right. And so this equals 0 when x is equal to negative 6. You're also going to want to check to make sure that the concavity actually changes at that point. That's not too hard to do. You'll find that we go from negative to positive concavity at that point. So the answer should be E, 9E. Okay, find the points of inflection and discuss the concavity of the function. First derivative is negative 24x squared plus 12x minus 8. Second derivative is negative 48x plus 12. So that means we have a point of inflection at 1/4. And we're going to want to test this on the number line. If you do, you should find that we go from plus to minus. So that means we should be looking at choice B, concave upward and then concave downward. Okay, find all relative extrema of this function, and we have to use the second derivative test here. So second derivative test, remember that it tells us that we have a maximum when our critical point has a negative second derivative, and a minimum when our critical point has a positive second derivative. Let's look at that. Let's find the critical points first. Derivative is 12x cubed minus 36x squared. So we need to factor this, right? So that means we have x equals 0 and 3 are our critical points. Okay. Well, now we're going to want to apply the second derivative test. So to calculate the second derivative, we're going to get 36x squared minus 72x. So the second derivative of 0 is going to be 0. So that's actually inconclusive. We're not going to have either maximum or a minimum at that point. We're going to have neither. However, when we plug in 3 into the second derivative, we're going to get, is it positive? Yes, it should be a positive number because this second derivative is also can be factored as 36x times x minus 2. And so if we plug in 3, we'll get a positive number, I think 108. So if it's concave up at our critical point, that means we have a relative minimum. So that leaves choice E. Find all relative extrema of this function. So same concept. Find the derivative. 6/7, haha. Where does this equal 0? That means our critical point is going to be x equals 0. Because 0 to the power of negative 1/7 is 0. Second derivative is negative 6/49 x to the negative 8/7. Sorry, I misspoke. X equals 0 is a critical number, but the derivative is not defined there, actually. So 0 to the negative 1/7 is actually undefined. However, the second derivative is also undefined, and so this is actually not going to work. We don't have a second derivative, and so that means we can't use the second derivative test, which means that we have to go back to using the first derivative test. So we're going to go to our number line and then see whether the function is increasing or decreasing on these two intervals. And then that'll help us determine whether this point is a relative minimum or maximum. So we can try stuff. If we plug in -1, -1 is going to give us a negative number because -1 to the negative 1/7 power is equal to -1. We have negative. However, when we plug in 1 to the first derivative, it's going to be positive because 1 to the negative 1/7 is equal to positive 1. So that means we should be having a minimum because it goes from decreasing to increasing, right? So we have a minimum at 0, -2. The graph is shown below for which value of x is the derivative minimized. So we have to think carefully here. Where is the derivative minimized? The derivative is going to be minimized whenever the slope of the graph is the most negative, right? Because the derivative simply corresponds to the slope And so wherever the slope is most negative, the derivative is going to be minimized. And that's clearly going to be at this point, because the slope of the tangent line at that point is the most negative anywhere on the graph. So we have x equals -2. Let's do question 14. Match the function with one of the following graphs. So this one is, once again, you have to use some logic to figure out which one matches the facts about the function that you can determine. So one good starting point is to first think about the horizontal asymptote of the graph. So we know that as x approaches positive or negative infinity, the function is actually going to approach 0. The reason is because the degree of the denominator is greater than the degree of the numerator. So that narrows out that narrows it down. You can't have A or D because the horizontal asymptote is not 0. We're going to be left with B, E, or C. There are some other things you can do. You can plug in some simple values. We know that when x is positive, the function must be positive. In other words, f of x is greater than 0 when x is greater than 0. So that narrows it down to B. All right, the reason why f of x is positive when x is positive, because this will be a positive number, and this will also be a positive number. So that narrows it down to B, because E doesn't work, since when x is positive, the function is negative. C also doesn't work, because when x is positive, there is a little stretch where the function is actually negative, and so that's not going to work. So we're left with B. It seems like Miss Lee did it a slightly different way, but that's fine too. It's just a little longer, and you can actually do the process of elimination faster. Okay, next question. We're going to do the same process. So first find the horizontal asymptotes. So here the horizontal asymptote is actually going to be 2. The reason is because the degree in the numerator and denominator is the same, and so we just take the leading coefficients and divide them. 2 divided by 1. So our horizontal asymptote is 2. And only positive 2, right? So not -2. So it eliminates A, eliminates B, E, and C. And we're left with just D. So that's pretty straightforward. Question 16, find the limit. Okay. Well, you can just think about it, right? As x goes to infinity, this is going to become a really big negative number, and this is going to approach 0. And so we're going to have negative infinity. This one I showed you guys in class once. To find the limit here, we want to take the leading coefficients. However, the square root adds some complications. That means that this is the leading term, 25x squared. However, the real degree of the denominator is actually just 1. The reason is because we have a square root of x squared. And so when we look at just the leading coefficients, meaning we get rid of the -5, get rid of the 5x, we're really going to have the limit as x approaches infinity of 4x divided by the square root of 25x squared, which is the same as 4x divided by 5x. So it's just 4/5. Question 18, sketch the graph of the function. Again, since we have multiple choice, process of elimination is totally acceptable. So let's think about, what can we think about here? We can think about the horizontal asymptote, right? The degree of the numerator and denominator is the same. So our horizontal asymptote should be 1/1, so 1. How about vertical asymptote? Well, the denominator can be factored as x minus 4 times x plus 4. And so that means our vertical asymptote is plus or minus 4. And at this point, we should be done because that is only true for graph A. Okay, 19. We're given a graph of the derivative, and now we want to sketch a graph of f. Okay, so first, this is kind of like the previous question, but now in reverse. So this derivative is equal to 0 at like 4.5 or something. So that means the graph that we're looking for should have a relative extrema at around 4.5. And only 4.5, right? Because that's really the only point where the derivative crosses 0. So that leaves us with d, right? Because we have a relative extrema at 4.5. Could be d, and that is the only one. Because all the other ones, this one doesn't have any extrema, and A, B, and C all have multiple extrema, none of which are at 4.5. So that leaves us with just D. Okay, calculator portion of the test. Um, in reality, do you really need a calculator? Um, maybe not really. The numbers are not awful, and I don't really need decimal answers. But you are welcome to have it if you'd like. Okay, find the length and width of a rectangle that has an area of 1,152 and whose perimeter is a minimum. So let's call this side x and this side y. We're given the area, so xy equals 1,152. We're trying to minimize f of x equals perimeter, so 2x plus 2y. Remember, we want to get things into only one variable, so let's rewrite this in terms of x. Y equals 1,152 over x. So that means we're really trying to minimize 2x plus, what is this, 2,304 over x. Okay, so to minimize that, we need to find the derivative, which is going to be 2 minus 2,304x squared. Where does this equal 0? Where an x equals root 1,152. Okay, we don't need the negative values. And so that means what are we looking for? Length and width. That means the length is going to be 1,152 square root, and the width is also going to be that. Now we have to use the second derivative test to prove that this perimeter is a minimum. So we're going to take the second derivative of f of x. That is going to give us, oh gosh, 4608 over x cubed, I think. Yep. And now we want to plug in that critical point, so square root 1,152. And we want to think about whether this second derivative is positive or negative. Okay, indeed, this is positive because we have a positive x value. And so that tells us that we have a concave up function when it's at the critical point, so that's a minimum. That is a minimum. All right, question 2. Find two positive numbers such that the sum of the first, call it x, and twice the second is 64. We're trying to maximize the product, f of x equals xy. So let's write y in terms of x, as usual. So y will equal 32 minus 1/2 x if you solve that out, which means that f of x is equal to x times 32 minus 1/2 x, which is also equal to 32x minus 1/2 x squared. So to maximize this, we're going to have to take the derivative. We'll be left with 32 minus x. That equals 0. when x equals 32. And so that's our critical point. And what does y equal in that case? Y will equal 16. That's my answer. 32 comma 16. Second derivative test. The second derivative is just -1, which is less than 0 for all x. So that means we have this is a typo, isn't it? It's supposed to say product. So that means we have a concave up function, and we really do indeed have a maximum because it's concave down at that point. Okay, some curve sketching here, isn't that right? How fun. Okay, x-intercepts. We have an x-intercept whenever the function is equal to 0. And so when does the function equal 0? X squared over x squared minus 4 equals 0, only when the numerator equals 0. So that's when x equals 0. So our x-intercept is going to be 0, comma, then we just plug in 0. F of 0 equals 0. That is also going to be our y-intercept, right? What is a y-intercept? That's just when we plug in x equals 0 into our function. So our y-intercept is 0, comma 0. What are the vertical asymptotes? That's when the denominator equals 0. So it's going to be x equals plus or minus 2. What is the horizontal asymptote? That is going to be y equals 1. That's because the degree of the numerator and denominator are the same, and so we just divide their leading coefficients, which gives us 1 over 1. Okay, calculating the derivative. We need to use quotient rule. So low d high minus high d low, low d high minus high d low over low squared. Now we just need to simplify the numerator. It's going to be 2x cubed minus 8x minus 2x cubed. Which is negative 8x over x squared minus 4 squared. So what are the critical points? The critical numbers are going to be whenever the derivative equals 0 or is undefined. So that's -2, 0, and +2. So we'll have to split up our number line like that. -2, 0, 2. And then we'll have to plug or test different values within those intervals within the derivative that we have. And we'll find this is increasing. This is increasing, this is decreasing, and this is decreasing. So the intervals where f is increasing going to be -infinity, comma -2 in the union with -2, comma 0. It's decreasing from 0, comma -2 to 2, comma infinity. Okay, don't forget you have to split it up at x equals -2 and +2 because the function isn't defined there. I don't think Miss Lee did that, but I guess that's fine. Okay, x coordinates of relative minima. So remember, in order for something to be a relative extrema, the function actually has to be defined there, right? So it can't just be any critical point. The function is not defined at -2 and 2, so those can't be relative extrema. The only possibility is x equals 0, and there we're going from increasing to decreasing, right? So that must be a relative maximum. So x equals 0 is a relative maximum. Now, the second derivative. Oh, so close to being done. Second derivative, low d high minus high d low. Chain rule here, right? Pretty annoying to simplify. So let's expand the x squared minus 4 squared. Um, Actually, there's a faster way. There is a faster way to do this. That is by canceling out one factor of x squared minus 4 from the numerator. So if we cancel out one factor of x squared minus 4, we are going to be left with this. And the denominator will become x squared minus 4 cubed. Okay, and so that means we have 3 points that we want to use to split up our interval. Is it 3 points or 4 points? Sorry, just 2 points. The reason is because this numerator never equals 0, right? Um, because if we tried to solve that, we would have x squared equals negative 4/3 or something, which is impossible, right? A square can't be negative. And so we only need to split it up where the denominator is undefined, so that's negative 2 and 2. And then if we plugged this stuff in to the denominator, we would find that this is positive, this is negative, and this is positive. So the function is concave up from negative infinity to negative 2, and 2 to infinity, concave down from negative 2 to 2. Are there any points of inflection? The answer is no. The reason why negative 2 and 2 are not points of inflection is because the function isn't actually defined there, right? In order to be a point of inflection, the point has to actually exist on the function. Okay, so which graph corresponds to all this stuff? We can probably just start looking at the vertical asymptotes, and that would just tell us that the answer is A, I think. Yeah. So A is the only one that matches the vertical asymptotes, and so we're done. Hello.
But I'm gonna set up the test dividers. I'm assuming you need those for tomorrow.